So we're ready to finally broach our final topic of the semester, which we've been kind of talking around a little bit, even though I think that we've cited it and maybe even used it at one point up until now. And that last topic is Stokes Theorem. So just as a reminder of what Stokes Theorem is going to do for us, Stokes Theorem is going to allow us to trade out a circulation integral in 3 dimensions for a surface integral on a 2-dimensional surface. And that seems like it's not a very good trade for us, given how challenging surface integrals can be. But there are some circumstances in which it actually does give us a nicer thing to work with. And one of the reasons it can give us nicer stuff, right, is that whereas in Green's theorem, when we have a closed curve in the xy plane, we have only a single way to fill it in to come up with a region to do a double integral for Green's theorem over. When I'm in 3 dimensions, if my curve is a 3-dimensional thing, there can be a bunch of different ways to fill in a surface in order to get a surface integral that gives us the same value as that circulation integral does in 3 dimensions. And so Stokes' theorem doesn't care how you fill in this surface as long as the boundary is exactly the curve that we hope to have, that we're trying to find the circulation around. And there's one sort of last caveat on how Stokes' theorem works, and that is that we have to decide again on an orientation for what is going to count as positive flux. How does the surface, in other words, inherit an orientation from the orientation of the boundary? So let's actually kind of start there and decide on that convention before we go forward and try to do anything more sort of high-powered with Stokes' theorem. I'm going to try to do this so that I can try to get into the shot as much as possible here. So just like when we were defining cross products and so forth in the first place, if we look at the orientation of the curve, so in this example, this curve is being oriented kind of going around this way, right? So it's kind of going, if we were looking at this from the top down, it looks like it would be counterclockwise. And so the orientation that we agree upon for the flux which Stokes' theorem is going to determine through a closed surface of which this curve is our boundary, and it doesn't matter what surface that is as long as the boundary is the one that we want, that if we point our thumb in the direction of the flux, then our fingers are going to be curling around in the direction of the circulation of the curve that we're looking for. So in this example, because my curve is circulating in sort of this fashion, right, then my thumb is pointing in the direction that we want to consider the positive flux. I hope that this is right with the camera looking in the way that it is at me right now. So right-hand rule takes my fingers in the circulation direction that we're interested in on the curve, and our thumb points in the direction of positive flux. So basically what that rule gives us is a relationship between what counts as positive circulation and what counts as positive flux. So that is what Stokes' theorem tells us. It is nothing more than the 3-dimensional analog of Green's theorem in 2 dimensions, right? That the circulation around a closed curve in 3-dimensional space agrees with the surface integral of the curl, the vector curl of our vector field, where that surface integral is taken over whatever surface we like as long as its boundary is the curve that we're trying to find the circulation around. So the last thing that we're going to do together over the next 45 minutes or so are just some examples where we get an opportunity to put Stokes' theorem into practice to evaluate a circulation integral in 3 dimensions as a surface integral instead. And as you might imagine, because surface integrals are nasty in general, the one time that was probably good, the one time we want to take this deal, is when either the circulation integral that we would have to do here is really hard, or if my vector field is really hard, but its curl, its vector circulation density, if you like, ends up being something really easy. Or at least that vector curl could be something really easy if we picked our surface accordingly. Like maybe picking a flat surface would give us a really easy expression for the vector curl, in which case this would probably be the right thing to do. Or maybe we can sort of inflate our surface or something so that it matches up exactly with a place where the expression of the vector curl is really easy, such that the vector curl ends up, having a really nice dot product with a normal vector to the surface or something. So it's not one of those theorems that you're going to be reaching for all the time, but there are certain circumstances where it really can make your circulation integral much easier. Or if you happen to be going the other direction, if you're taking a surface integral of a vector field that you already know is the curl of something, then replacing that surface integral with a circulation integral can also have a lot of benefits. One of those benefits being that you don't have to do a surface integral. So let's look at a couple examples of this together to wrap up the course, as it turns out.